Okay, so can you see my screen?
Yes.
Okay, perfect. So yeah, we were talking about a scalar product, right? Okay, so basically a scalar product is defined as this thing, and it gives you just a number, and that's why it's also called a scalar product, because it's just giving you a scalar. So an example of a scalar product is work, because work is defined as f dot d, which is the dot product or the scalar product. Scalar product basically means, so suppose I have a vector f, it is in this direction, and it so suppose that this is the force that I'm applying, and I'm moving an object by applying this force this way to the right, and let's say it is this vector d. Now what happens is you need the only component of force that could be responsible for the object to move in this direction is this component. The vertical component has absolutely nothing to do with moving an object in this direction. You agree with that, right?
Yes.
Okay, so that's the reason that we have f cos theta and this d. So which is basically f dot d, right? Because this is how the dot product was defined. Okay, so anyways, that was the reason for the dot product to, basically that's the definition of the dot product. Okay, so dot product has some properties. Let me just fix the screen. I guess this much zoom is enough. Okay, so it has some properties, or you can say there are some characteristics of the dot product. So first of all, they follow a commutative law, which means that the vector A and the vector B will commute with each other. So there is another way to write that. It's just A, B, and these square brackets are known as a commutator. And you can say that if this is 0, this means vector A and B commute, and that's the property of a dot product. So the dot product basically follows the commutative law, which means that A dot B is the same as B dot A. But I'm sure you know that this is not true for a vector product, and we'll see that. It also follows the associativity law, which is called the association law, which just means that if I have some constant with vector A, so I'm scaling my vector A with some constant m, and I'm scaling my vector B with some constant n, then that just means that I can scale this dot product, I can scale it with the product of m and n. And now for unit vectors, they have some properties. You're aware of unit vectors, right? So they are basically
Yes.
so they're the perpendicular directions that we can associate. So they're independent of each other. I is independent of j, and j and so on, like I, j, and k, they're all independent. So the dot product of these two gives you 1. Basically, it means
Right.
that
0
so
degrees.
I,
So cos is 1.
yeah, exactly.
Mm.
So it means that I is just pointing in I. Obviously, it would be pointing in the direction of I, so it's 1. Similarly, you have for j and k as well. But I and j, they do not give you
Right.
1. They give
Perpendicular.
you 0. Yeah, exactly. So they're exactly. So no component of I lies along the component of j. So it means that I and j are orthogonal. Okay, so next is that you can find the angle between two vectors by this expression, where theta is cos inverse of, okay, so I wrote it in a very compact notation, so I'll just tell you what it means. It means this
It's
thing
A
is
dot
just,
B
yeah, ax
over AB
bx.
magnitude, right?
Yeah, exactly. So that's what this is. So you have the components are summed together, and then you have the magnitude of AB. Okay, perfect. So now we can move on from this thing. Let me, okay, so no, we have it over here. Okay, so the next thing is, of course, it's a vector product. It's also called cross product, and it's defined as the curl of A and B. Okay, you can also call this curl A B. Anyways, it's the cross product of vector A and B, and it's defined as AB sine theta, but with a unit direction as well, right? So what is N? N is basically, so if I have this plane, suppose I have a plane and I have these vectors A and vectors B, you can say here I have vector A and B. N is simply the direction which is perpendicular to this plane. So any vector that I can draw like this, all of these vectors are N vectors, N hat, right? So your cross product is defined as AB sine theta N hat. And clearly you have, this means that there is some direction. And so it's also, that's why it's called the vector product. Now, similarly, vector product have some properties as well. So first of all, the vector product of A and B is not the same as the vector product of B and A. And we can check that as well by choosing any arbitrary vectors A and B. Then the for unit vectors, we have I cross I and J cross J are 0. And similarly, K cross K is also 0.
Right.
Right. And so if the two vectors A and B were perpendicular to each other, then A cross B is just A, B, and the unit vector N.
Yes. Okay.
Okay, perfect. Now, well, this is not really a property. It's just a cyclic rule from which you can basically remember how can I find the cross product between I and J and K and I and so on, right? So it's are you aware of this? Are you aware of this thing? How this circle works basically? Okay, so I'll just I'll tell you. You have I and you have J. So suppose that I want to find the vector product between I and J, right? So that's I cross J. What would that be? So you're going in this direction. The arrows point in this direction. So you're going in this direction. You meet K, but again K does not change your direction. You still move in this direction to get to K. So this means that this is plus K hat. However, if I wanted, let's say you wanted J cross I, right? So what would happen in that case? In that case, you'd be moving from J to I. So you go J, you meet I, and then you go to K. But to reach K or to go forward from K, you have to go in the opposite direction because K was in this direction, but you're going in this direction. So J cross I hat is, so the sign changes basically. That's negative K hat. So you can compute all your I cross J, I cross I, and all of those from this cyclic diagram. Okay, so next.
Sorry, I got disconnected. 1 second.
Oh, my bad. I did not even I could not see that you're disconnected.
Yeah, this is just understandable.
Okay, so you're familiar with this diagram,
Yes.
so how you can use this to compute the. Okay, perfect. So the next thing is the vector product between two vectors A and B. It's it's defined as this determinant, and you can you write I, J, and K, and then you write the vector A components first in first row, then the second vector you write it in the second row, and then all you do is well, at least this is how I do it. If I have to compute the I hat component, so what we'll do is we'll write it like this, equal to, and then with this J hat we'll put a negative sign basically. So there will be a negative, and then this components, and then plus, and these components. So first you write this thing, and then what you do is to compute the I components, you forget I and the entire column, and you forget this entire row. And then you compute the determinant of AY BZ minus AZ BY, right? So you have AY BZ minus AZ BY. Similarly, if you want to compute, let me use this stroke eraser. So similarly, if you wanted to compute for this J hat, what you would do is you would forget these and you would always keep forgetting this row. And then you would compute the determinant of what's left. So AX times BZ minus AZ times BX. So we're just computing the determinant, right? And likewise, you would do the same thing, you would do it for K as well. So to compute the K part, you'll just forget the entire column that contains this K, and you'd forget this row, and then you'll compute the determinant of what's left. So that's AX BY minus AY BX. Okay, so is that clear?
Yes.
Okay, perfect. So, okay, we still have 7 minutes left, but I'll have to open another file so that we can continue. Just give me 1 second.
We didn't do the cross product in A levels, but I had some idea.
Oh, right. So, what I just told you right now, how to compute cross product of two vectors, is it clear? Is it completely clear?
Yeah, it is clear, but it's lengthy. In exam, we won't have much time.
Yeah, it
See how the
is
questions are, right?
Yeah. Yeah, it is kind of lengthy, but once you practice some questions, you'll get used to it, and it will be it'll be pretty easy. So, okay, so let me find the next file. Okay, here it is. All right, I'll share the screen. Weird. Okay, all right, so well, moving on, we'll move on to the equilibrium and forces part, basically. So we'll start with torque. You have any idea about torque? I'm sure I think you do.
Yes.
You're familiar with torque. Okay, perfect. So, it's something that is going to produce angular acceleration. That kind of a thing is called torque. So it's basically a physical quantity. And if it produces angular acceleration, then you define it as torque. So if you consider this example where a diagram, basically, you have this wrench, which is basically, I don't know, if you can tighten, or I think this at this point it's unscrewing this bolt over here. So you're applying a force in this direction, and the only force that is contributing, you can say, to unscrew this bolt is this F sine theta, or phi, F sine phi. And the distance from the center of the bolt to the point where you're applying the force, or the axis of basically you understand that this would be the axis of rotation of the bolt, right? And this would be the axis of rotation for the wrench, because this is the axis of about which the bolt is going to perform the angular acceleration in this direction, or rotate, basically. So the only component that is responsible for that is the sine component, sine phi component. The horizontal component, this force, so the force which is being applied in this direction, does not contribute anything to unscrew this bolt.
It is
And so
because Is it safe to assume that all the vector quantities will be with sign and all the scalar quantities will be with cos?
Yeah,
Okay.
you can say that, because the cross product is defined, you remember we just saw that how the cross product was
Right.
defined, right? So wherever you have basically you have two vectors, so let's say a vector, b vector, and these are vectors and they have some sign of angle, whatever angle it is, right? And then you have a direction. So this is basically a vector. It's a vector product basically. Yeah. So in this case, then we have this R cross F is defined as the torque. So we have RF sine phi. So which is this component. So only this just means that only this component contributes in performing the angular acceleration at this point, right? And the dimensions, or you can say the units of torque, are Newton meters. Now, it's very interesting to note that these units are the same as the units for work as well. Okay, so next we have the effect of torque. So what effects do you think a torque would basically have on a system? I should not say say it like that. What things would affect the torque basically? If you look at the expression for torque,
Right.
obviously, yeah, the force that is applied and to what distance from the axis of rotation that force is applied, that would change the value of torque, right? So the magnitude of the force and the distance between the line of action of force and the pivoting point, which is this one.
Right.
And the line of action of force is this axis. So is that clear?
Yes. Okay, this is and the angle. Okay. Okay. Is there any difference between moment or torque, or the same, or they both the same thing?
No. There is a difference between moments and torques, and we'll get to that as well.
Torque is for like a rotating object.
Yeah, even moments is for a
Or
rotating
right?
object, but yeah, but moment is actually the analog of mass. So whenever you have a motion that is translational, you understand what that means, right? So linear motion.
Back and forth. Right.
Yeah, so it's so there's no rotation going on in that.
Yeah,
So
like a
in that
seesaw.
case, yeah, exact. No, yeah, seesaw. No, what I mean is a translational motion. So so there's no rotation in a seesaw. There is, well, it's not really a rotation. I guess you're just going up and down if you think about it. So yeah, so in that case, we have something that's mass. But whenever we involve rotation, then the analog of mass is used, which is the moment of inertia. So are you familiar with this expression where the kinetic energy of for a rotational object is half I omega squared? So if you just compare this is for rotational, right? And if you compare this with the linear kinetic energy for something that is moving linearly, it's half mv squared. So it's just that this is the analog of mass, and omega, angular velocity, is the analog of the what is this called, tangential or linear velocity, right? So there is a difference. There's actually a big difference between moment of inertia and torque. In fact, you can relate torque with force. In linear motion you have force, but in rotational motion you have torque. So torque is the analog of force basically. And the other thing that would be affecting the value of torque is the value of sine theta. So it depends. So basically, you can also say that the angle theta would change the value of the torque as well. I used theta over here, and in the figure it was phi, but I think you get the point, right? So just the angle.
Yes.
Okay. So I guess we have the time is over. Let's end this here, and just let me know. Are you? Is this okay now? Because I think I did. Obviously, according to your suggestion, I tried to speed up things a bit. Are you understanding or getting everything?
Yes. What's remaining?
Sorry, can you repeat?
What is remaining in this chapter? Can you scroll down?
Oh, there are only a couple of things remaining. Equilibrium is the important thing that is still left, right? So only equilibrium part is left, and we'll just talk a bit about center of gravity. And so we'll complete this chapter as well. So basically, we have different kinds of equilibriums, 2 different kinds of equilibriums. We'll talk about them, and we'll then finally talk a bit about center of gravity, and then we'll be done.
Okay. I'll be sending you my email. You can share my recordings.
Yeah, I'll even share these notes with you. You can find these notes on the website of Mega Lecture as well. They're updating it. So there's that section where you have notes. I think it's notes and worksheets. It's called notes and worksheets. You can go down, you'll find in the physics section, it says Basel's notes. So when you go in that, there will be all these notes will be available. So in fact, I think more the next topic notes will also be available over there, some of which I'm covering. Those I have at least completed so far. You can go through them as well. So it would help speed up the process even more. You're getting the point, right? Yeah. So we'll so yeah, you can find the notes over there. You can send me your email, and I'll see with these. I'll share these lectures with you as well.
Okay.
Sounds good. Okay, perfect. Okay, so I think can you let me know your name, please?
Sayyid Ahmed.
Syed Ahmed. Yeah. Do you know who was the other person? What was their name? Did you get the chance to see their name?
Yes, but 1 second,
I
let
think
me just check. It was Abdullah something.
Abdul. Okay. Okay, perfect. Okay, then see you in the next class, right?
Okay.
Okay, thank you so much.
Allah Hafiz.
Allah Hafiz.